Good evening, everyone. Can anyone please confirm am I audible to you? And oh, you have left the meeting. Okay, so please, I hope I am audible to you, and my screen is also visual to you. Uh, so welcome to the big seven of this lecture, wastewater treatment and recycling. The course instructor for this subject is Professor Manoj Tiwari. He is from IIT Kanpur, and my name is Manitnam Prakash, and I am a PhD scholar in Department of Civil Engineering. We meet every Tuesday from 7 p.m. to 9 p.m. online via Google Meet. The link for which has been already shared with you, and the recording of this session are being uploaded on this YouTube channel. The link for which has been also shared with you. So in week 7, we will be looking on these five topics. 1, 2, 3, 4, 5. Yes, 5 topics. That is secondary treatment process. So if you recall the previous session, we were discussing about, first we discussed about wastewater, then we discussed about what are different components of wastewater, then we discussed about different treatment process, then we went into detailed discussion of each part of treatment units. As we started with preliminary treatment, uh, then uh, then primary treatment, then we went to secondary treatment. So in primary treatment, this is a part of secondary treatment. Also, secondary treatment, generally we talk about degradation of organic matter. So you can imagine that if you recall the last session, we were discussing about that the degradation can occur in two conditions, that in presence of oxygen and in absence of oxygen. So we know that in presence of oxygen, when the degradation happen in presence of oxygen, it is known as aerobic condition, and in absence of oxygen, it is known as anaerobic condition. So we will be discussing about anaerobic treatment of wastewater. Then we will be discussing what are the different steps that is involved in anaerobic degradation process. Yes, and then we will be looking into some application. Then one of the treatment unit which uses, like in, we have seen that we have, for primary treatment we have sedimentation tank, then we have activated sludge process in for which we have aeration tank and resupply of sludge and all these things. Similarly, for anaerobic treatment of wastewater, we have UASB reactor. We will be looking into detail what is this UASB reactor, and finally other high rate anaerobic process and biogas production. So we will be seeing that how, how this anaerobic process is useful, and how it treat our wastewater and what are its different bioproduct and all these things. Okay. Hmm. So this is the this slide has been taken from last lecture only, that we have shown you this preliminary treatment, then primary treatment, then secondary treatment. We have already discussed about this in second lecture. We were discussing about this thing. Third, fourth, we were talking about this thing. And then in last slide, last lecture, we were talking about the secondary treatment, that the use of microbes and all these things, where we have seen how microbe degrade our organic matter and the population of microbes, how population of microbes changes. So a part of secondary treatment, that is degradation in presence of, in absence of oxygen, that is anaerobic condition. We will be looking it one by one. Okay. So again, and some there is some discussion of sludge process. So in each process, that is whether it is primary treatment or secondary treatment, we have this sludge production. We have seen that in primary sedimentation tank we have this tank thing, and the bottom of there was a mechanism to collect the sludge, and this sludge has to be managed. So again, in next lecture we will be discussing more about sludge processing, how this sludge is processed and all these things. Similarly, in waste, in secondary treatment, we have seen that once the food is degraded, all the microbes died. Lot of microbes are, lots of sludge are being generated. So somehow we have to process this, and somehow we have to convert this sludge into some useful thing. Okay, so we will be looking into that also. Then in upcoming slide we will be also looking into advanced treatment also, but in this session we will be just focusing on this secondary treatment, that is anaerobic condition. Okay. So again, some of the recap, because all the questions, most of the question in this session are theoretical question, that is most of the, I think 11 question, total 15th question are there, out of which 11 question are theoretical question, and most of them are very easy question. You can expect this type of question in your assessment and all these things. So we have second, first we will be, we have already shared about this thing, that is secondary treatment process, and the first topic was introduction to anaerobic treatment of wastewater. So in way, first I am trying, I am trying to do give explanation of the topic, and then one relevant example. Okay. So in wastewater secondary treatment, first we have to know what is secondary treatment, which we have already discussed. Is designed to remove the organic material remaining after primary treatment. Anaerobic treatment is one type of secondary treatment where microorganisms break down organic pollutant in the absence of oxygen. This process is energy efficient and produces biogas, a mixture of methane and carbon dioxide. Okay. So I hope everyone is clear with this thing. What is this anaerobic treatment? That is a secondary treatment where microorganism. Remember that any process that is occurring within the microbes in absence of oxygen will be referred as your this thing, anaerobic condition. This process is energy efficient and produces biogas, mixture of methane and carbon dioxide. Okay, so we will be looking how this methane of, there is series of what do we call it as, a series of reaction that helps, in which these microbes break down, and finally we get methane and carbon dioxide. Methane is used for energy production and all these things. I hope everyone is, mm, everyone have this idea. Okay. A typical example of this treatment is in typical municipal wastewater treatment plant. Aerobic digestion is used to treat sludge generated from primary and secondary clarifier. We have already discussed this. The anaerobic microorganism degrade the organic matter in the sludge and producing biogas. Generally, this will be done on sludge and all these things, and will be producing biogas. Remember, this methane is known as biogas. Okay. Then coming to the second topic, that is anaerobic degradation process. Anaerobic degradation occurs in several stages, that is hydrolysis, acidogenesis, acetonogenesis, and methanogenesis. So remember, I have missed. I will be discussing what is this hydrolysis and all these thing. So in aerobic digestion, these four process mainly occur. Okay, now finally first will hydrolysis will occur, then acetogenesis will occur, then acid acidogenesis. Remember, miss, there will be some hydrolysis. Miss, I think everyone is understanding with hydrolysis. Then there will be acid formation. Then there will be acetone formation, and finally methane formation. Each step involves different microorganisms and process that break down the complex organic matter into simpler compound, ultimately producing biogas. Okay, now so we will be looking just before it's after second class, but second slide. But I will discuss what is this. What do we call this hydrolysis? Okay, now so as you can read from uh, this. Slide, that hydrolysis is the initial step in anaerobic digestion process. During hydrolysis, complex organic matter. Remember, complex organic matter can be in the form of CX. It will contain CHNO. Okay, na? All this carbon, nitrogen, hydrogen, and oxygen. Okay, na? So what will happen that during hydrolysis, complex organic matter such as carbohydrate, proteins, and fats are broken down into simpler molecule by reaction of hydrolytic enzymes. Okay, now so there are some enzymes. Remember, all these things are happening in presence of some microbes. Okay, now so at the end of the lecture, I'll be showing you what are those microbes. What miss generally see this hydrolysis occur. If you remember this, if you suppose this is a starch, a kind of organic matter. So simple hydrolysis is happening, that is reaction with water, but it's not that simple that this is there and this water is there and it is breaking into glucose. Okay, now so there is a complex process. Okay, now so this complex process occurs with a series of bacteria, like some bacteria with a with a series of bacteria, not a like it's not a simple process. Okay, now this occurs with the help of some bacteria. What are those bacteria? So if you want to see those things, please just stay till end and I will be discussing. Okay, now these enzymes catalytic break down the large organic molecule into a smaller compound such as sugar, amino acid, and fatty acid, which can be further metabolized by other organisms in the subsequent stage of anaerobic digestion. Okay, so what will happen? The first step has occurred. Reaction with water has happen. A larger molecule has been broken down into a smaller molecule. Okay. So now what will happen? That second step is acidogenesis. That is generation of acid. So acidogenesis is the second stage of anaerobic digestion following the hydrolysis. In this stage, a simpler molecule produced during hydrolysis. So you can see this carbohydrate has been broken into simpler molecules. So that is sucrose is broken into glucose. Okay, such as sugar, amino acid, and fatty acid are converted by acidogen into volatile fatty acid. Now, what will happen that this will be converted into some volatile fatty acid, alcohol or hydrogen or carbon dioxide through fermentation reaction. So there will be some reaction again here also. It's not like a simple reaction. A series of bacteria will be acting on those a series of bacteria will be acting upon those organic molecule and that will be degraded. Everywhere you have to assume that some bacteria are involved. Okay, this intermediate product serves as a substrate for subsequent stage of anaerobic digestion and methanogenesis. So you can see here we can see that some bacteria. So see here you can see you may by seeing this reaction, someone can see that it's simply converting into ethanol and carbon dioxide. Then that what I have said, but it's not like that. Bacteria is acting on this glucose and there is some reaction happening in presence of bacteria in absence of oxygen. That's why this is getting converted into ethanol, that is a kind of alcohol. And this process is also known as ferment. I don't recall, I don't remember whether this is called fermentation, but you can see that CO2 and ethanol are producing. Then the third step is acetic acid or acetogenesis. Okay, now so acetic acid is a type of volatile fatty. So you can see that this is a acetic this. So now what will happen that this ethanol which is there, it will convert into acetic acid, means acetogenesis. Some kind of acetone related product will are getting formed, that is produced during the acetogenesis of anaerobic. It is formed from the fermentation of simple organics such as sugar and other carbon by acetogenic bacteria. Again remember, a kind of bacteria that is known as acetogenesis. Acetic acid is important precursor for production of methane in final stage of anaerobic digestion. So what will happen that this acetic acid which has been formed, you can see from this example that this ethanol is in presence of CO2 is getting converted into acetic acid and this hydrogen, and this will be finally reacting, finally helping in production of CH3 COOH. Production of this acetic acid will be converted into methane and CO2. Okay, now so, hmm. So, methane genesis, that is formation of methane is a final stage of anaerobic digestion where methane is produced from degradation of organic compound by methanogenic archaea in oxygen-free environments. Remember, as it is anaerobic condition, that's why there is oxygen-free environment. Okay. Methanogenesis utilizes the intermediate product of acetogenesis such as VAT, alcohol, and hydrogen as substrate to produce methane through a series of biochemicals. So there is like, remember, it's not like that first has occurred, then first has come. This, remember this step that it will whatever has been, it will also used as mm, utilize the intermediate, whatever the intermediate product has been formed in previous three steps, that will be utilized to finally converting our acetic acid into methane. Okay, now methanogenesis is a critical step in anaerobic digestion as methane is a primary component of biogas which can be captured and used as renewable. The whole aim was to collect some, to produce something useful from our um, uh, waste. Okay, no, wastewater. So that's why this anaerobic digestion has been done. So at the end of the treatment we are getting this methane gas, and that can be used as a source of energy. Okay, now so remember, whatever happening is, we are mm, we are just making sure that mm, that we are getting at the end of at the end of treatment, we are getting something useful product, byproduct from the those treatment process. So here you can see that we are getting this methane. Okay, now so all the reaction, this is just a simple reaction, that this methane, this starch is getting converted into acetic acid. Okay, now first hydrolysis occur, first this hydrolysis occur, then then this acid formation has occurred, then acid formation to acetic acid, and finally this acetic acid is getting converted into methane and CO2. Okay, na? So at the end of the lecture, we I will be showing some bacteria also which are responsible for this kind of conversion. Okay. So coming to the third topic, what is its application? So anaerobic degradation is characterized by ability to treat high strength waste with high organic load. So remember, more organic load will be there, more methane formation will be occurring and all these things. This is just another thing. This is simple thing also. Miss, but anaerobic digestion is to treat. Remember, miss, generally it is suppose if you have, see, because we are also, miss, like this is normal process. Like you can imagine why we are using anaerobic degradation. Suppose you have high organic matter in your wastewater, so you require high amount of oxygen. Okay, now providing high amount of oxygen is not economical option, and that much oxygen is not, because you can, if you see the data how much oxygen is getting consumed for degradation of per kg of wastewater, then it will be coming very high. Okay, now so providing that much oxygen is not a good idea. So it is generally suggested that we can go for anaerobic digestion where there is less need of oxygen and all these things. It is commonly applied in treating industrial wastewater, agriculture waste, and municipal waste. This biogas because see at the end of the treatment, we are getting this biogas which can be used as a source of energy. In dairy farm, manure from cow can be processed in aerobic. This organic material is manure broken down into produce biogas, which can be used to generate electricity or application. Is widely used in food and beverage industry to high strength wastewater with high concentration of organic matter. So these are some of the examples. Okay, these are not related to wastewater. These examples are normal example. Maybe in that, in maybe in that, maybe a dairy plant has their own anaerobic digester and all these things. Okay. So, so one of the reactors. So remember in treatment in primary sedimentation tank, we were discussing about this thing. Mm, Sedimentation tank. That we have this sedimentation tank. Okay. We have this sedimentation tank. Hmm. And whatever the primary sedimentation tank process will occur here only. Similarly, for secondary treatment process, that is activated sludge process, there was this aeration tank, then this sludge collector was there, and from here there was recycling. Okay, so this kind of things were there. Similarly, for anaerobic treatment, we have in wastewater we have this UASB reactor, that is upflow anaerobic sludge blanket. Okay, now so it is a reactor is a popular high rate anaerobic treatment process in the system. Water flow upwards. That's why the name is upflow through a blanket of granular sludge where anaerobic microorganisms degrade the organic pollutant. The biogas produced in the process forms bubble that helps to mix the sludge and wastewater. Okay, so you can I will be showing the picture also. A USB reactant can miss the means generally if you have high organic matter in your wastewater, this can be used. Okay, the chemical reaction, the same anaerobic digestion reactor where same thing happens here. Like say this process happened, there will be some first hydrolysis will be there, then acid formation will be there, then acetone formation, and finally methane formation. Okay, so I will be just showing what is this flow. This is neither suspended growth nor attached. It is retained biomass reactor. Remember, we have talked about suspended, that is activated, then trickling filter. All these were this thing activated or suspended. But here you can see a picture of this UASB. Water is coming from here. There is this sludge blanket is here, and there is some other arrangement, and we are finally gas dome which is able to collect gas, that is methane, and finally we have treated wastewater outlet and we have sludge outlet. Okay, because once the treatment has happened, see remember this is a blanket which will contain anaerobic bacteria. Okay, so what is that wastewater influent to the from the bottom of the tank, that is from the bottom of the tank we are sending wastewater. The sewage flow from bottom to top of the water, and the sewage we know that this wastewater will contain high amount of organic matter, and it will flow from bottom to top. Okay, the wastewater passes through a sludge blanket containing mainly inert material with attached anaerobic bacteria. So there will be some inert material will be there, and it will attach with anaerobic bacteria maintained in a fluidized state by the upflow flowing sewage. So these are always in means in liquid form only. COD reduction of sewage taken place during the upward flow. Sewage reduction. COD means you can see. Remember this COD because we know that once the this loading will decrease, then the amount of COD and amount of BOD will decrease. Okay. Methane and carbon dioxide is produced due to anaerobic biodigestion. This gas bubble travel through upward reactor and collected by the gas dome. COD reduction of wastewater means whatever the reduction has happened, it will be COD of the methane produced. You can just remember, you can just imagine that imagine that your organic matter contain only this thing. Okay, now So whatever the COD of this will be there, the COD of the methane formation will be equal. So you can, there is one mathematical expression also, that per kg, suppose if we assume, it's not mathematical expression, generally it is assume that, suppose we have some, a question will be there that a wastewater contain this thing CO, CXHY and something, and a COD will be given to you. So by help of this several you can write down all the reaction, and you can see much for reduction of 1 mole of that compound, how much methane is getting produced, and based on that you can also calculate the COD. So that's why it is said that COD of the, whatever the COD of this thing is, will whatever the COD of the degradation has occurred, it will be equal to the COD of methane form. Okay. Huh. Uh, so and then we have one special. So remember, what will, suppose a gas bubble has occurred, and in gas bubble it is high chances that those sludge can also get attached and it can go up. So for that we have one special separator, that in arrangement, that is glass liquid solid separator, GLSS, helps to prevent sludge particle attached to the gas from escaping from the reactor effluent. Sludge is wasted once or a day or even more frequently. Okay. So I hope this is clear to you. What is sludge is coming from here? It is going through anaerobic, then a gas is formed, and to prevent to prevent the to prevent the that if any sludge is in trap in this bubble, then it can easily, then this will prevent, and it will only allow gas to go, not the sludge particles. Okay. So as usual, we have seen in secondary treatment and primary treatment also, that they have their own advantage and disadvantage. So in this UASB has also their its own advantage and disadvantage. Okay, so I will be discussing one by one. So this is a common picture of UASB. So if you are visiting any wastewater plant near any industry, so in Kanpur we have this Jajmao area where there is a lots of tannery industry, and that contain very high amount of organic load, because you can imagine that for tannery industry they use the skin of animals, and a huge amount of waste is produced, which is so that's why actually it's not in Kanpur only, but I have been to two or three wastewater treatment, and there I have seen this UASB. So it will be a very large, it will be around, it will be very big. You can see in the picture also that how how big is this arrangement. So this is USAB, hmm, sludge blanket, yes. So you can see how it's quite big. Okay. So coming to the advantage, that you can see that there is no, as you can see that all the process are occurring in the absence of oxygen, so there is no need to provide any oxygen, so there is no need to provide any aeration, so that's why energy requirement is very low. Operation of the reactor is straightforward, the skill manpower not required. So if means it's very simple to operate, so there is no need to hire, yeah, to miss, there is no need of this such a special manpower to a special manpower to run this UASB. Okay. Then the low sludge production. So we can most of the organic matter means sludge. See, it has two meaning, low sludge production, because whatever sludge is getting produced, either it means it's used for this thing, manure and all these things. So all at the end of treatment we have several um, useful bioproducts such as biogas, then whatever the break after degradation, we have very useful this thing, what do we call, um, useful organic matter which can be used as a organic manure. Okay, so but apart from the advantage, we have several disadvantages, that is poor effluent quality. Whatever the water is coming is of is not that much, it's of poor quality, means poor BOD, poor COD and all this thing. Unreliable performance due to periodic sludge escape with the treated effluent. So what is happening, that you can say that suppose if sometimes we have already given GLSS, but there are some chances that it will escape and we will be getting a poor quality of treated wastewater. Okay. um, Methane recovery is low for low strength domestic wastewater and hence unviable. So remember, you cannot use this for to treat our domestic waste, because the first condition to for this UASB that it should have high organic matter, high organic load, more organic, more COD. Now remember that this we have in our domestic waste, we have organic, high organic load, but it is miss for domestic, the structure or the arrangement is huge, that if you are providing a wastewater which has not I don't recall the exact number, that how much minimum COD, minimum organic content should be there. So but it should be high, that's a sufficient amount of methane is being produced. But now imagine that you this UASB are generally made for a wastewater containing high organic matter, and you are supplying a wastewater which contains very less amount of organic matter. So what will happen, that the methane which will be produced, and that was your main objective, that to collect as much as to collect more and more methane gas. Now if that criteria is not fulfilled, then it will be a loss for the treatment owner, that who means generally government is there. It will be not a viable option to treat this wastewater. Okay, ineffective at low temperature, external heating needs to be. So this is another thing, that at low temperature, then again we have seen that we see, not only we have to remove organic matter, but we have to see, remember we have told you that it will be, so what happens, that a need of temperature is there, because this there is some particular temperature is required for anaerobic bacteria to act. So the temperature, there is a question related to the temperature should be between 25 to 35 or 40 degrees Celsius. Okay na. So only in that temperature this bacteria will act. So if temperature is very low, so what will happen, that that bacteria will die. Okay, then no nitrification of the effluent. So remember that our organic matter contains C, X, Hy and nitrogen also. But here you can see that whatever the process is occurring, uh, it's occurring only to this thing, what do we call, um, it's occurring only to carbon present, but nothing is happening to nitrogen. So there is need of nitrification also, which is not happening here. Poor removal of pathogens. So you can see that in this picture, we can see that there is no any facility to remove the pathogens, which can be, pathogens are harmful bacteria. Okay now, so there are high chances that harmful bacteria will be coming out of from the treated water outlet. Okay, sulfate present in wastewater is primarily converted into sulfide through action of sulfur reducing bacteria. Now, suppose you have this sulfur reducing bacteria which is present in along with bacteria. Okay, so now what will happen, that this sulfate will convert into sulfide. and metal sulfide are precipitated which give a black color. Production and escape of H2S gas produce odor problem. So remember, this H2S gas has its own problem. So now we have sulfate in our wastewater also, and it has been converted into sulfide, and sulfide may be getting escaped as H2S, or it can be precipitated with some metal. So okay, so what happened that once this happens, this production of sulfide reduces the methane formation, hence COD removal by methane formation is removed. So now imagine that instead of methane we have H2S, which is not useful, and this has a very bad smell, like rotten smell. This sulfide remains in water, and it exerted intensely when released in the nature and uh, water bodies. So there will be some problem if your wastewater has subsulfate. On the whole, anaerobic treatment of the domestic wastewater is infeasible unless accompanied by comprehensive aerobic polishing treatment. So no, suppose if you now it is recommended that if you are doing anaerobic digestion, once what will happen that all the a huge amount of organic matter has been converted. Okay, now so what you need to do that as soon as the aerobic digestion has occurred, so there will be a polishing with the aerobic treatment, aerobic bacteria. So in that way, what will happen that first of all the burden which was there in our wastewater, that is a high amount of organic matter, so loading has decreased. So now if you are providing enough oxygen and enough bacteria which acts in presence of bacteria, so you can treat your wastewater in a more efficient way. Okay, so that's why it is recommended, because you can see we have only three advantage, these three advantage, but a lot of disadvantage. Okay, so anaerobic treatment is not recommended for high sulfate. Also we have discussed that what can this sulfate do to our facility. So if your wastewater is if wastewater contain high amount of sulfate, there are high chances that you cannot stand here, because it will be very pungent smell, like rotten egg smell. Anaerobic treatment is not recommended for high sulfate wastewater due to associated problem with sulfide production. Okay, so this was all about USAB. Those who have joined, I think one person has joined right now. So we were discussing about anaerobic digestion. Okay, so if you have any question, you can write in chat box, or you can just unmute yourself and you can start speaking. I hope I am audible to you. Okay, so coming to the last topic, that is before going other high rate. So this thing which we have already discussed, that my main aim is the main byproduct of this anaerobic digestion is this production of methane. So apart from UASB, there are other high rate anaerobic process such as anaerobic filter, anaerobic baffled reactor, expanded granule sludge bed. These are generally not used in not in India. I don't remember, but this USAB reactor, you can see if you visit any treatment plant, you will be seeing it. Generally, if that treatment plant is in near any industry, for example, in Kanpur, we have a huge UASB because of this tannery industry. Okay, their system are designed to treat water, and so this thing, the overall chemical reaction which is there, that this will be getting converted into methane in an aerobic reactor. We have this formation of CO2 and CH methane gas, and we have seen that this is not a simple process. Okay, so the whole process is this four process. First is hydrolysis, then acid formation, then acetic acid formation, and finally methane formation. Okay, so all the discussion which I was going to, so this was just a recap of what has been, yeah, what has been discussed. Yeah, maybe you will be seeing this video in future. Okay, so these lectures in future. So coming to the questions, uh, so just try to answer it. If you have miss, if you have gone, if you have attended my lecture, yeah, if you have gone through, if you have gone through lecture material, and I think I have discussed enough. Miss, I have discussed in detail what are different process. So just try to answer it, and we will discuss it one by one. Okay, so the first question is to identify the correct statement regarding the anaerobic system for wastewater treatment. The first process is anaerobic system require less energy, rather produce energy in form of biogas. Anaerobic system are high efficient in removing nutrients such as nitrogen and phosphorus. So remember when we were discussing about advantage and disadvantage of this UASB, we were discussing. Okay, na? So yes, we have got one answer, that is A. So remember, this is advantage and disadvantage. Remember, it's correct that no oxygen, no energy is required, low energy. But you should know why low energy is required, because there is no aeration required. Why no aeration is required? Because all things are happening in absence of oxygen. As there is no need of oxygen, there is no need to provide any air. Okay, so that's why this thing, and we have seen that only whatever the reaction is happening, it's happening in the for our organic carbon only, nothing. I have chosen one example also, that suppose if you go through some books, like Metcalf and Edith, you can see that they have you I don't recall the example, but you will see that nothing is happening to nitrogen is as it is. Okay, only carbon is getting converted into methane, but nitrogen is getting, it is not getting reduced, and or nothing is happening to. And similarly for the phosphorus. So so this was one of the disadvantage of our no nitrification of the effluent. Okay, so the question is, yes, the answer is correct. The first statement is correct, that it require less energy and produces energy in the form of biogas, that is CO2 and methane. Okay, and is highly efficient. No, it's very low efficient. There is no nitrification. So you can see that I have given a small explanation also, that in aerobic system do not indeed require less energy as compared to aerobic. This is because they do not require aeration. Remember, why you should always able to answer why it is requiring less energy to for treatment process. Anaerobic system produce biogas from composed of methane and CO2 as a byproduct of decomposition of organic matter by anaerobic macroorganism. This biogas can be used as energy source, making the anaerobic system advantageous in terms of energy production. Coming to the second statement, anaerobic systems are generally not very efficient in removing nutrients like nitrogen and phosphorus. They are more effective at reducing organic matter and production of biogas. Organic matter means they are mainly focused on carbon. Okay, they are not they are not considering any other element which is present there. Especially nitrogen often require other. We will be saying in upcoming lectures, that in maybe in big 8 or big 9 you will be saying how this denitrification and other thing occurs. But when we are discussing about anaerobic reactor, we are only mainly focused on treatment of our organic matter. So I think I have forget to add animation. If you have just try to uh, just try to answer this question. In biogas produced during anaerobic treatment, fraction of methane is higher than fraction of CO2. Fraction of methane is lower than or fraction of methane is equal to the fraction of CO2. Any of the two, that is methane or carbon dioxide, can have higher fraction than other. Okay, so yes, the correct answer is A. Typically, biogas produced in aerobic digestion contains sufficient proportion of methane and CO2, with methane being primary component. Generally, it is say that, and you can write the chemical reaction also. Suppose you can take any example, like suppose we have this thing. Okay, na. So if you add up everything, and if you try to balance out all the moles and molecules, you will be seeing that high amount of methane is getting produced. So as your for your own curiosity, you can just do a calculation that how much methane is being produced. So, say take an example of sucrose only, sucrose as your organic matter, and then write each and every step. See, if you write direct conversion to this methane and CO2, you will come to know that equal amount of methane and equal amount of, for example, this thing. If we look at this reaction, we will be seeing that, saying that equal amount of methane and equal amount of CO2 is getting produced, but this is not a case. Okay, now actually I have written it in mis like in direct form, but a complex thing are occurring at the end of, because here you can see that we are using this C6H12 and O6. We are starting from second step. The first step is this sucrose will be getting converted into glucose. This is more, this is not a complex. Remember, the first step is hydrolysis, where this a complex material is getting converted into a smaller product, a smaller molecule. So this glucose is a smaller product. Okay, so don't go on this reaction. Okay, so for your better understanding, I request you to write down reaction on your own, and just try to see how much percentage of methane is forming and how much percentage, and you will be seeing that 50 to 70% are uh, methane, and generally this carbon dioxide are very less. So the answer is correct, that is a methane fraction of methane is higher than the fraction of carbon. Coming to the third question, in acid formation stage during the anaerobic digestion. So remember, we have four steps: hydrolysis, acid generation, acetone generation, and finally this we have methane formation. So go to each and every option. That is, methane and carbon dioxide are formed through the conversion of hydrogen and acetate. Hydrolyzed compounds are converted into short chain intermediate compounds such as propionate and butyrate. Complex polymers are broken down into monomers and oligomers such as sugar and amino acid. Lower chain volatile fatty acid are converted into hydrogen and acetate. Okay, so just to go through each and every, if you need any assistant, like if you want to see the slides, previous slide, just tell me, I will go back. Okay, na, but take your time and try to answer it. Just go through the basic whatever I have said you, like what is methane formation, what is acid formation, what is acetone formation. Okay, so uh, sorry. So remember, miss, I have given the correct answer will be uh, B, that is hydrolyzed components are converted into short chain intermediate compounds such as propionate and butyrate. Okay, so acidogenesis is the second process. We know that in our following hydrolysis. In this state, the hydrolyzed complex organic matter such as carbohydrate are further broken down by acid. Okay, bacteria into simpler organic compound, alcohols and gases. The process produce short chain volatile fatty acids such as propionate, butyrate, and acetate, as well as hydrogen and carbon dioxide. So the correct answer is B. Okay, na. So just for your reference, you can see this. I am going again. You can see we have complex organic matter, that is a starch, that is getting converted into glucose by hydrolysis and some bacteria. Remember, each step some bacteria are acting. At the end of, I have already said that I will show you which kind of bacteria are converting, uh, which kind of bacteria is acting during hydrolysis. So stay, miss. Once all the questions are finished, I will show you the name of those bacteria. Then we have acid formation. So once this complex has been converted into a smaller smaller molecule. Again, these are converted into acetate. Yes, related. So there we are calling proponite and all these things. And what will happen that again this will be converted into acetic acid, that is a lower chain of fatty acid and all these things. And finally this is getting converted into methane. Okay, so the question was very simple. If you have gone through the lecture, it was very simple question. I think I have done this mistake. Generally, I do not do. Hmm. So again, if you have gone through lecture, this represents again. This is very simple question. I think I have already shown you the answer. So you can see that this is like methane formation. Okay, na. So remember they are calling at acetoclastic methanogenesis because from acetate they are forming methane. But in simple book, if you refer any book, there will be simple process will be there: hydrolysis, acetogenesis, and finally methanogenesis. That okay now. So but as the question was in that way that they have used this term, but remember there is one other term, hydrogenotrophic. So there must be, so here we are producing methane from acetate. Okay, that's why we have answered C. Okay now, I don't remember what is this, so let's just for our, I also am not gone what is this thing. Okay now, let me just search. So that uses molecular hydrogen as a source of metabolism. No, these are not miss. And uses hydrogen. Huh? So if so, I think this is the name of bacteria. Similarly, remember this this aceto must be this must be also a uh, bacteria only, where they are converting acetate into AC. Okay, na. So as it is using acetate, that's why we have this answer. If it had been a use of hydrogen and with some organic matter they are converting into this methane, then we would have been calling it as a hydrogen hydrogen trophic methanogenesis. Okay, so this is a process where acetate is converted into methane and by this archaea. So this, remember this this is the name of Miss, you can just methanogenic archaea is a kind of bacteria which is getting converting this into this. Okay, na. The reaction is a key step in the final step of anaerobic digestion. That's why answer is C. Okay, na. So, try to answer this question. Just ignore this thing. Okay. Oh, no. Which is the major concern with anaerobic process? Lesser startup time, lesser efficiency for nutrient removal, sensitive to toxic compound. So again, if you have paid attention to the disadvantage and advantage part, so they are asking that which are the major disadvantage. Okay, na. So if you have paid attention to the slide which I have shared few minutes ago, you will be able to answer it. Take your time, analyze each and every option, and finally give your answer. A and B. It's single choice. Which of the following is? So it's a single choice question. You cannot mark two option. So, D the correct answer. So again, so our first question, if you remember this thing, first question, question number one was also similar to that, nutrient removal. So of course, it is less efficient. So B will be also answer. Then we have so sensitive to toxic compounds. So we have seen that. if if we have sulfate in our system, if we have sulfate in our system, then there will be some problem. So again, sulfate, presence of sulfate is not good for our this anaerobic thing. Okay now, and it has been seen that in presence of some toxic material, what will happen that the anaerobic bacteria may also die. Okay now, so we will let's discuss one by one. The A option is longer startup time. Anaerobic system typically have a longer startup time compared to aerobic system because the growth rate of anaerobic macroorganism is slower. So establishing a stable microbial community for effective treatment can take several. So this is a like property of the anaerobic bacteria, that they take a huge amount of time for their growth. Okay now, so it should be in sufficient quantity, a sufficient, it should have sufficient number of population, so that it can start degrading our organic matter. So it typically takes a long time. So A will be also our answer. If you have any kind of doubt, you can ask. Not really. Is there any culture? Is there any culture available? Let me see your question. Is there any culture available for speed growth? Yeah, we can always introduce some kind of culture for speed growth, but here we are talking in most economical way. We don't want to see if for a culture also, miss we have you have to produce first you have to produce that culture, that itself will be a economical option. So here, whatever discussion we are doing, we are discussing dealing in most economical way. So there is always a option to speed up the process, but that will require a extra cost. So we don't want to do that. Okay now. So yes, there will be some culture. There will be always some culture for speed growth, but we don't want that. Okay, so that's why we are we want to invest as much as less. I'm sorry, we want to invest in bare minimum for treatment and all this thing. Okay, so that might be due to fund and all this thing, but we don't want anything culture thing. Then we have lesser efficiency for nutrient removal. Then of course this we have already discussed. I'm dealing with 20 mld STP. Okay, so 20 mld STP. So means now it's depend upon how large is your anaerobic digester. Like what is the retention time and all this thing. Suppose if your retention time generally whenever this USAB, let me show you one data of USAB design, that how much uh, retention time and all these things are considered during where it is. It's like a theoretical example only, but you will have some idea like where did it go in same. You will have one idea like USB reactor design, that what are different data which are being used for treatment. Uh, so it's for only 10 mld, which is much lower than your. Okay now, so here you can see that the uh, where the this retention time hour. So retention time we have kept at for 6 hour. Okay now, so if you want, you can just take a screenshot of this. It might help you maybe in design. You have to evaluate your. But remember that this dark. Remember, we have two things. Actually, in here it is written, given, and calculated. Okay, now. So whenever we all know that when we are designing something, first there will be some parameter which will be given to us, and there will be some parameter which will we have to calculate, and based on that, we have to uh, we have to evaluate. Yeah, we have to select some parameter for design purpose. So I hope I have answered your question. Still, if you have any doubt, you can just say it, or just type in chat box, or you can unmute yourself and you can start. you can just I will be going through the full for you can take a screenshot of this complete design. I hope you have taken a screenshot. But just you can see that in USAB, like how much this thing is there, how much methane can be produced, depending upon we know all these things, how much COD is incoming, how much design flow is there. So similarly for your 20 MLD, you can just estimate. So remember there is something actually it's a theoretical example, but in real groundwater situation may change also. But this will give you one idea how this UASB reactor has been designed, keeping in mind that how much methane and this thing can be formed. I hope this is was clear to you. Coming to the this question which we were saying that we were discussing, like which is the following suitable, there was one if you remember the disadvantage of anaerobic digester, that at low temperature this bacteria die. So what is the minimum temperature for for this efficient? So try to everyone, I those who have joined few minutes ago, I want you to participate in question and answering. So I will be presenting question one by one and try to answer it. So we have one B option. Okay, good. So anaerobic bacteria typically, so remember we have this every range of temperature is known as some name has been given to every range of temperature. So generally the temperature between 30 and 40 degree is known as mesophilic range. This is the most common and stable temperature range for anaerobic digestion. Most anaerobic bacteria thrive in this range, leading to efficient breakdown of organic matter and biogas. So this is another temperature range where can occur more rapidly, though it requires more careful management as system is more sensitive to flocculation and potential inhibition. So remember that we have two temperature range where this anaerobic bacteria can work. But remember that we are talking in the range that we don't want any external not external manpower, external management to manage our system. We are just so because this temperature is also considered good for our bacteria, but at this temperature you have to do another management also, that there are high chances that you have to take some kind of risks, and we don't want that kind of risks. So generally this 30 degree to 40 degree is selected. Okay, on another hand we have this 5 degree to 10 degree which is low, and this will kill all the microbial activity, making the system very inefficient. Then we have 60 degree to 70. Obviously this is typically thermophilic. Remember all the range would likely to determine to it will also kill our microorganisms. So therefore the final answer for this question is b, that is mesophilic range. Remember, you have to either say the temperature or say the name of the range, that is mesophilic range. Okay, so again we have seen so actually I think during my presentation I did not care about this. I forget to add animation. So again when I was showing this UASAB, I was discussing about GLSS. So a question is again related to GSS, if you have paid attention. So try to answer this question. If anyone have any if you have idea about GLSS, then answer. If you don't have idea about GLSS, I can repeat it, like just I can do those who has not those who have joined recently, just those if you want to so we have two answer, that is one is not visual. What is not visible here? Is my screen? You all are able to see my screen, na? Someone has said that not visual. I think Subhas, please, miss. I think if everyone is facing this problem, then I have to do something. But if it's your own problem, then I think you should check your system, Subhas. Subhas, yes, Subhas. Oh, he has left the meeting. Okay, so I just for one, just to show what is this. So this was our. This was our, remember, this was our UASB reactor. So this water was going from here, then through this sludge blanket, and this gas was. Then there are high chances that, so you can see that to sludge particle attached to some. So there are high chances that what do you have? At the end of the session, we have some numerical question. So we go like this thing only. First we discuss theoretical question, whatever, and at the end of the lecture we have some. I think four questions are related to this numerical question. We will be discussing that questions also. So have, so okay. So this is GL. So so GLS, glass liquid solid separator in USB reactor is crucial component designed to separate three phase, that is solid, biogas, and effluent. Okay. So this separator allow the biogas to rise and escape from the top of the reactor while preventing the biomass, that is sludge, from being washed out with the effluent, and the effluent, which is treated liquid, exists on the top of the water. So we have our answer, that is D, that is solid biogas as well as effluent from the mix. Okay. I hope this is clear to you. The one who has just said answer B, Barun, the answer will be D. Okay. Then uh, during anaerobic treatment, high ammonia concentration in the reactor. Answer is already given to this, so I will just read it out. Okay. So suppose if you generally this is also a concern of anaerobic. So remember, if phosphate and nitrogens are there, so these are typically nutrients, and their removal due to that efficiency will be very low. Okay. So this high ammonia in anaerobic can be toxic to methogenic bacteria, archaea, the microorganism responsible for production of methane in final step of anaerobic digester. Ammonia toxicity can inhibit the methogenic activity, leading to the reduction overall efficiency of methane production. So this ammonia is toxic to this. That's why there was one more question that uh, we have discussed in question number 5 or 6, that will their efficiency will be same in presence of some toxic thing. So that is related to this thing also. So therefore the correct answer is C, that is reduce methogenic activity. Hmm. Coming to the question number 9, that is just try to match, just try to, this is a match the, you have to different treatment system, and what are its different examples. So based on our previous discussion of the previous lecture, and based on the discussion in this lecture, just try to answer it. First system is low rate anaerobic treatment system, then high rate anaerobic system with attached growth, then high rate anaerobic system with suspended growth. Anyone with any answer? B A, B A C, B C A. So B A C. The correct answer is A. So let's discuss one by one. Okay. Hmm. So first we have low rate anaerobic treatment system. Okay, then low rate anaerobic treatment system is that septic tank. The septic tank is a classic example of low rate anaerobic treatment system. They operate at low hydraulic retention time and provide basic treatment by settling the solid and allowing anaerobic digestion to occur at a slow rate. So remember this septic tank design and all these things that generally anaerobic condition are maintained due to depth and all these things. So these are very low rate anaerobic thing. Then we have high rate anaerobic system with attached growth. Then this will be anaerobic. This is related to anaerobic filters. So anaerobic filters are high rate system where the biomass is attached to a medium, wastewater flow to the medium, and the attached biomass treats the wastewater. Okay, and then we have this thing high rate anaerobic suspended growth. Okay, so this is our UASB. So remember, this is UASB not completely suspended growth, and neither it is uh, attached growth. So they have used this term and there was no other option, that's why we have to match this. What I mean by that, this is this USB is not a suspended growth or so generally the growth which has happened after it is a retained biomass reactor. So what will happen that it is getting suppose consider this as a compartment, okay na. So all the biomass are retained here. It's not like that, it's not as we have seen in our trickling filter that there will be a media and on that some bacteria will be attached, and in suspended activated sludge process we have seen that all the bacteria will remain suspended, organic matter will be there, organic matter will come and it will degrade it. But but in this USB we are retaining our biomass in this blanket, okay na. So that's why it is known as retained biomass reactor. So I hope this is clear to you. But for this question we have used this term, but I have also clarify that as we have don't have any other option, that's why I am matching this. And we know that for in up USB there is a high rate. Means we have to we have seen that we are dealing with 10 mld, 20 mld, maybe higher, and we have to treat that at that huge amount of time. So there is the rate should be very high. Rate means when we are talking about rate, we are talking about the rate of degradation. Okay, so high rate aerobic system where biomass is in suspended form, along it's not suspended, it retained form. Okay, now there will be some correction. Why I am telling suspended form, because this was option. Right now I don't have option. But suppose if I am teaching someone about USB, then I will never use the term, use the this term of suspended for USB. I will always use the term retained. There is a difference, suspended, retained, and I hope this is clear to you. Along for a high rate of treatment due to efficient contact between wastewater and biomass. So the correct option will be A, that is BAC. Okay, BACA. Again, we have question number 9. The collection of biogas from municipal is rare due to. Again, we have I have already miss. Just try to answer this question. Take your time and try to answer it. If you have any kind of doubt, you can always ask. Okay, don't miss. We will be discussing these things. But if you have any kind of doubt, Sorry. The collection of biogas from municipal wastewater treatment is rare due to getting municipal wastewater for enable is challenging. Technology are not available for collection of biogas. Methane recovery and purification process is costly. So we will going by one. While municipal wastewater can be treated anaerobically and biomass can be produced, the challenge lies in cost effectiveness of methane recovery and purification. The process of capturing, cleaning, see whatever the gas is getting produced, we cannot directly use it. Okay, na? We have to purify it because it might contain some other gases also along with. It will be in very less amount. But suppose if we want to produce energy from something, then it should be pure, not something with contamination that it is less efficient in energy production. Okay, so that's why the process of capturing, cleaning and utilizing the methane products can be expensive, which often limits the implementation, especially in municipal wastewater treatment plants. So therefore, the see getting municipal to anaerobic challenge. This is generally not significant issue. Municipal wastewater is commonly treated anaerobically, especially in larger facility. Technology are not available. The technology for biogas are available, but their application may be limited by economic consideration rather than technology feasibility. Therefore, the correct reason is C. Methane recovery and purification cost is costly. Okay, then we have more five question. Mostly this is also not theoretical question only, but from next onwards we have this numerical question. Okay, na? So just try to answer this question. Take your time and try to answer it. Please write. Please come up with any answer and just any thought on this question. Any answer? It's very simple question. Effluent from industry A and B have equal COD. COD was representation of this amount of organic and inorganic content. Okay. However, TOC is 840 milligram per liter in the effluent from industry A, while 1250 milli in from industry B. If the effluent are treated anaerobically, okay. So remember, Miss. Now, which what will be? Sorry, for methane formation, what we require carbon. Okay, and TOC, the full form of TOC, total organic carbon. Okay, now TOC is total organic carbon. Okay, so remember, more organic carbon, more methane formation will be there. So out of this thing, industry B has more organic carbon, so obviously the percentage of methane in B will be higher. Okay, because it has more organic carbon. Industry A flame will higher. Wrong. Industry B will be yield higher methane percentage in the biogas. Both A and B will same methane. So answer will be, I think uh, I think I said something wrong. At lower TOC with same COD imply the higher portion of organic matter in more efficient conversion of methane. Total oxygen amount. I think I said something. Just let me check once. It measures the amount of carbon in organic compounds. In this case, both industry have same. A has lower TOC, has a lower TOC as compared to industry B. A lower TOC which seems to give that high proportion of organic matter in industry A effluent is biodegradable. Okay, total organic carbon, leading to more efficient conversion into methane during anaerobic digestion. I think I will hold on to this question because I think I have to recheck it. Miss, I don't know why I have written this. Correct answer is A. A lower TOC with COD imply a higher portion of. I think the answer will be B. I don't remember, but again I will recheck it, and if you in next class I will try to rectify. So I'm not discussing this question number 11. So coming to the numerical question, those who were asking for this numerical thing, the first just try to solve it. Take your time and try to solve it. Okay, now the consider a stoichiometry anaerobic conversion as shown in the adjacent figure for a 60-meter cube effluent volume USB. Suppose we have one USB of volume this much, treating 2 mld industrial effluent having inlet COD of miss, volume of the USB is 160 meter cube. Then the waste which is coming is of 2 mld, that is 2 million liter per day, and the COD is 1200 milligram per liter. So remember, uh, some data is given that in effluent we have 15 kg COD in the effluent, then 5 kg is getting converted into sludge in the form of mass, then 80% is getting converted into biogas containing 75% methane. Remember, only 80% is getting converted into biogas, but only 75% is methane. Okay, and this methane which is there, the volume of CO2 is 10 to power minus 10 to power 9 meter cube, and similarly for methane is 28 in meter cube. That is similar to 280 kilowatt. Okay, so based on these data, just try to answer it. The first question is simple question, that volumetric loading, that is volumetry organic loading rate of the reactor in kg COD per minute. What is the organic loading rate? Okay, now so you have to consider all the COD in the form of organic, and you have to find the what is the organic loading rate. Take your, so there is two option, either I can wait for you to solve it, or either you can, I can show you the solution. Anyone if anyone is solving, just write in chat box that he is solving, or I will show the solution. Please explain the solution. Okay, so remember, I will be going one by one. To calculate the volumetric organic loading rate, we need to determine how much COD is being loaded into the reactor per unit volume per day. Okay, so we have already given, we have been given this uh, uh, hmm. We have been given this data that the volume is this much, flow is 2 mld, which can be converted into meter cube per day, and the inlet COD is 12 milligram to 1200 milligram per liter. So first before calculating the loading rate, first we have to calculate what is the COD per day. Okay, now because final answer we have to give in COD per kg only. Okay, the COD is flow rate into COD concentration. So we know the flow rate is 2000 meter cube per day, and the COD concentration is 1200 milligram per liter. And we can convert in milligram to kg, and meter cube, it is 10 ki power it, sorry, just 1 minute. We know that this milligram can be converted into kg by the power of 10 ki power minus 6. Similarly, meter cube will be converted into liter by 10 ki power 3. Okay, na? So combining these two, the overall there will be a factor of 10 to the power by 3 and liter. So if we convert it into, then we will come out to know that 1200 milligram per liter, it will be 1.2 kg per meter cube. Okay, because there is a fraction of 10 to the power minus 3. So total COD will be 2000, that is flow into 1.2 kg COD per day, that is 2400 kg COD per day. So this much of COD per day is coming into our system. Okay, and we have to volumetric organic loading rate means per volume how much COD is coming, and we know that volume is 160 meter cube, 160 per meter cube. Then the volumetric loading rate will be 2400 divided by 160, that is 15 kg COD per meter cube per day. Okay now, volumetric loading rate of the reactor is 15 kg COD. So this was our answer. Okay, so again going again we have one other question, as you are saying that we have to show the solution only. So now we have, so it's, if you now see this problem, that it is saying that at the effluent we have this 15 kg COD in effluent, then we have to calculate this thing, and remember that 80% is getting converted into biogas and 5% is getting converted into biogas and 5% is converted into biomass. So depending upon this data, you have to calculate this thing, COD of the treated fluid. So whatever, see initially how much COD was coming, 1200 CO 1200 COD, that is 1200 COD was coming into our system, and so 1200 milligram per liter of COD was coming into the system. Now you have to find how much COD is going into system. Okay now, so remember this is like this, don't get confused that 15 kg COD in effluent, like, but you have to calculate per unit volume, that how much per unit of volume the COD is coming out. Okay now, means how much treatment, you can say the other question can be in this form, that what is the efficiency of this digester. Okay now, so just try to understand. So you, we can see that 80% was getting converted into this thing, biomass, and 85% sorry 80% was getting converted into biogas, and 5% was getting converted into this thing biomass. So the reactor remove 85% of COD from the influent. So the COD remove can be calculated as inlet COD into efficiency, and the COD remove is how much, 1200 into 0.85, because we know that 75% and 80% and 5% are getting converted into other form, and those, so whatever the remaining COD will be there, it will be coming out of our system. So inlet COD was 1200 milligram per liter, COD remove was 1020 milligram per liter. So in the effluent we will be receiving 180 milligram per liter. So you can just, we know that the efficiency was 85%, and based on that we have calculated our COD effluent. Okay, just you can make a box also, that coming incoming is 1200 and outgoing is 180. Okay, another question is daily sludge production in the reactor. Now remember how much, which one will be responsible for sludge, biomass will be responsible for sludge, and 5% are getting converted into biomass. Okay, and you know how much COD is coming, so based on that thing we can calculate how much sludge is getting produced. Okay now, so remember COD this was now means how much biomass is there, that is 100 kg in the form of COD. 5 kg sludge is produced from 100 kg COD. This is already written in the question, that 5 kg sludge. Okay, flow rate is this thing, inlet COD is this thing. To calculate this, this thing we have already calculated how much COD is coming, and we came out to know that 1200 COD per day, kg COD per day is coming. Okay now, so this thing can be, I am just recapping it, that 1 meter, this thing flow rate is this thing. So total COD entering the reactor is 200 this flow rate into milligram per liter divided by this thing, just this is a conversion unit. Okay, so we came out to know the total COD entering in the reactor is 2400 kg COD per day. Everyone is getting what, see, one time we are using this COD milligram per liter, that is the parameter of wastewater, but we are also knowing that how much in the form of this thing, when we are representing in the form of mass, we are just saying simply 100 kg COD. Okay, if you have any kind of doubt, you can just ask me, just don't get confused, that's all. And we know that 100 kg of COD produce 5 kg of sludge, and we know that per day we are producing itna kg of 2400 kg of COD. So the daily sludge production will be 2400 into 5 by 100, that is 120 kg per day of sludge. This was just a simple conversion. We know that how much COD is coming, how much waste is getting generated. In question it is written. We have just multiplied the whatever the parameter that was given to us. The last question is the amount of power produced per day in form of CH4, that is in form of methane. Okay, and in question it is written that per 100 kg of COD, 280 kilowatt power is getting produced. Okay, and total effluent in the 24, we have already calculated previously that 2400 kg per day COD is getting in our influent. Okay, to determine the power produced, if 100 kg of COD produce 280 kilowatt, then for 24 kg of COD will be just a simple unit conversion, and we will know that per day we are getting 6720 kilowatt per day of power. Okay, so still we have around 20 minutes. So if you have any kind of question, yeah, if you want me to discuss anything in particular not related to this topic, maybe previously discussed topic, then I will be happy to discuss it. If I am aware of that topic, condition apply. Or if you want to repeat it something, yeah, I can show something related to this. So if you have joined initially when I was discussing about this methane formation, so I have just written out the reaction, but what are those bacteria which are involved in different conversion, I will be showing that thing. You have two option, either ask something, yeah, I will continue showing something. Sulfur impact on anaerobic digestion. Okay, there is two discard. There are two impact. First is that what happens that if suppose metals are also present in your wastewater, suppose some heavy metals are present, so sulfate, am I audible? Hmm. So generally two problems are there. So it's written here. First I will read out and I will try to explain it. Okay, na? Sulfate present in wastewater in particularly converted into sulfide through action of sulfur reducing bacteria. So see, sulfur reducing bacteria is there in our, will be there. Okay, na? Because it's simple redox. There will be some electron donor and electron acceptor. So here sulfate is in plus SO4 2 minus. Here it is in plus 6 form, and H2S it is in minus 2 form. So it is coming from minus 6 to minus 2. So by some electron exchange it can easily come, and there will be some bacteria present in the system. So what will happen that if sulfate is present, which is present, mostly present in our wastewater. Okay, especially if it is coming from industry. Okay, na? So sulfate, if sulfate present in wastewater partially converted into sulfide through the action of sulfur reducing bacteria present in UASB reactor. Metal sulfide, now condition apply that if apart from sulfate your metal, your wastewater also contain metal. So what happened that this when this metal comes in contact with the sulfide, they precipitate, okay, and they form a black color substance. Okay, the metal sulfide are precipitated, which often gives effluent a black color. So if I- this will be our first problem, that somehow a metal is present there, it has combined with sulfide and it has produced a black color, and if you receive the treated wastewater, you will see that it is in black color. The second problem is production production and escape of H2S gas produce odor problem. Now remember what happens, suppose metals are not there, so the high chances are there that it will combine the hydrogen ions present in the water, and it will escape in the form of H2S. And you know that H2S is a very um, means it has a very pungent smell of rotten egg, which is very famous. Okay, so H2S is highly corrosive. Production of sulfide reduces methane formation, and similarly this thing, there will be a problem of pungent smell, and other problem is that this production of sulfide will reduce methane formation. Hence, the COD removal by methane formation is reduced. Hence, this conversion, what was our main objective, that to reduce our methane, to convert by to collect methane and to produce energy, won't be fulfilled. This sulfide remain in water and is exerted instantaneously when released in natural water bodies. So I hope these are two three problems. First is it will form a black color, it will give a pungent smell, it is highly corrosive, and it also reduce our methane formation. Hence it will be reducing the efficiency of UASB. And when it comes in contact in water, it generally spread in, means it can also contaminate our water and all these things. Okay, I hope this is clear to you. Any another doubt? Any another question? Someone was asking what okay, okay, if no one is asking, then I will show you something. H2S, yes. During anaerobic condition of municipal water, HS formation is high or low. If sulfate is there, it depends. If suppose there is no metal, then high chances that it depends upon the parameter. In general, suppose if there is no metal, heavy metal present in your system, then there a high amount of H2S will be. And generally, if generally heavy metals are not present, so if I have to answer your question in a general way, then yes, it will be high formation of H2S, high amount of H2S also produced. Okay now, but but the first condition which arises, that our wastewater generally, where are those, where means this sulfate are present in very low amount, then generally this problem is not seen. But I will give you one example where this problem is seen, that is in Kanpur. First, miss, if for your answer you can say, if sulfate will be present, now your question has two three precondition thing, whether does your wastewater contain sulfate. And as you are talking about municipal water does not contain any kind of sulfate. Okay now, so the production will be very low. Means there is no sulfate, so that's why there is no production of H2S gas. Okay now, so now, means which kind of now if this question will be, does anaerobic condition of industrial wastewater uh, H2S formation is high or low? In that case, it would be very high. But for municipal water, the first question is that whether your wastewater contain sulfate or not. The question is this: if your wastewater contains sulfate, then yes, H2S formation will be there. Are you getting it what I am saying? Okay, sir. Apart from our topic, what is the problem called? Screening after grit chamber. Can we install a screening after grit chamber? Okay, can we install screening after? No. First, you have to place a screening chamber, then grit chamber. Because a screening chamber are to remove larger boulders, particle, and maybe particle having. See, the grit chamber name itself suggests that uh, grit, there will be a removal of grit particles are in the range of 1 mm to not 1 mm, maybe 3 mm to 5 mm. This will be considered as a grit. Okay na. And the screen are to remove larger particle, maybe bold, maybe some rocks are there, maybe some large high, very heavy particles are there. And generally a screens are, see, our wastewater contains many things. So this preliminary treatment is like, we want to remove, we don't want to give loading, extra loading to uh, upcoming treatment unit. Okay na. So that's why we have to install a screening chamber, then grit chamber. What is the purpose of installing a screen chamber? If you are installing grit chamber first, then the first problem will be there, that your grit chamber, the purpose of the grit chamber was to remove the grit particles. Now imagine that in grit chamber you are providing that water which contains grit particles also, and some larger particles also, a particle having larger particle size than grit particles. Then it will be just increasing the load of grit chamber. And with time it will require high maintenance. With time it will be not a economical option. So first we have to remove the larger particles. Once the larger particles are removed, then we will go to remove the smaller particles. And once the smaller particles are removed, then we go to the removal of suspended particles. Then there is this process. So just to make things economical. Now the question can be this thing also, that why we are also placing a screen chamber and grit chamber. We can just directly pass our water into this settling tank. Yeah. Then that will won't be economical process now, because it will, see, when we design something, we assume something, that in this part, in this tank, these things has to be removed. Okay na. So now if we are not following our norms, if we are not following our objective, then efficiency will be decreasing of each treatment unit, and it won't be economical viable option. I hope I have answered your question. Any another question? If you have any another question, just write in chat box. Ha. So this is anaerobic biodegradation. So I was saying the first step is this thing. Are you able to see this PDF? I hope you are able to see this PDF. Hmm. So see, I am just here to see. I was saying that I will be showing the different kind of bacteria which are involved in conversion. So first step was our acid formation. Okay na. This is like this is more organized way. So so we have complex organic carbon which will be there in form of C, X, and other oxygen. So what will happen that a series of, before converting into acid, that is acid for, before going to, so what will happen that on this, the bacteria which occurred is known as liquidizers, okay now, which is anaerobic in condition and are heterotrophic. I hope you are aware with heterotrophic, autotrophic, okay. So what is its energy source will be this or complex organic matter, food source will be organic carbon, and electron acceptor will be also this organic carbon, and the byproducts will be protein, carbohydrate and lipids. So this process is known as hydrolysis. Simply complex organic matters are getting converted into a smaller molecules. And now what will happen that on these smaller molecules, fermenters will act, that will convert into acid, and this process is known as acid formation, okay na. And here what will happen that here the fermenters are anaerobic heterotrophic, okay na. So remember, these, what are these liquidizers? These are anaerobic heterotrophic. So any bacteria which has this nature will be present here. Any bacteria which has this nature will be present here. Okay. Energy source is again this thing, food source, electron, and bioproducts will be amino acids, sugar, fatty acids, and alcohols. So this is like a acid formation. Once this acid formation has occurred, then we will have this acetate formation, okay na. Third step is, on third step we have this OHPA, that is hydrogen producing acetogens, that is also anaerobic heterotrophic. I am assuming that you are, if you have attended my last lecture, I have discussed this heterotrophic, autotrophic, and all this thing, okay na. So, and this is very common, there is no big rocket science in knowing heterotrophic and autotrophic. So again, what will happen that first it will be it will convert, OHAPA will convert into this this acetate, okay na. And along with acetate there will be some bicarbonate hydrogen will be also there, and that will be converted into acetate with the help of this homoaceto jo homoacetogens HA, that is also in anaerobic and autotrophic in nature, okay na. So everywhere you can see the bacteria has a autotrophic is changing, but the nature of bacteria is always anaerobic, that is in absence of oxygen. So they are using this hydrogen as a energy source. Here we are using organic carbon, okay na. And what will happen that, see, what if some bicarbonate is there. So remember, um, for formation of acetate, either it can be in the form of by conversion of this alcohol which was formed during acid formation, or if some bicarbonate are present in your wastewater, which is always present. Bicarbonates are always present in your water, because with time COD is getting dissolved in our system, and sorry, CO2 is getting dissolved, and CO2 is getting converted into bicarbonate, and the pH range of our wastewater is between 7.5 to 8, and in this range this bicarbonate is, so this bicarbonate is also converted into acetate. So this process is known as acetate formation. Once this acetate has formed, then it will convert into, either it will be getting converted into bicarbonate methane or simple methane, okay now. So suppose if this NHOM is present, remember when we were looking into this reaction, this seems very simple, that these are getting converted into this, but people, but when they are working, suppose if someone is working in this anaerobic thing, they have to deal, because see, this reaction is not a simple reaction, because the, the role, some a significant role is being played by organic matter, or microbes present is there. So that's why it is always preferred that you should know the nature of microbes and all these things, okay now. I hope you are getting what I am saying. I am not going in details. I am just showing how things are, how things work. Okay, now just to give you idea, so that you can be more curious to know things, to know like to go in the depth. Okay, if someone asks, if some anyone can answer that in anaerobic digester four process are there. What which bacteria is responsible for those process? You should, if you are a good wastewater engineer, yeah, good environmental engineer, then you should know this thing. Generally, no one cares about it, but suppose if you are in teaching line, and generally these type of question are expected, because it's very simple. Four process are there, but why four process? This should be answered. Okay, so again, I am saying again, I'm not going into detail here. You can see that if methane is formed from acetate, then it is known as simple methane. Or you can see along with methane, some bicarbonates are also present, and these bicarbonates are getting converted into methane with this HA. Okay, now so there is this two-way process. Some acetate are getting directly converted into methane, as here you can see. But along with acetate, some bicarbonate is also producing. So, so first bicarbonate will get converted into acetate by this HA, by this process, and then this acetate will get converted into methane. So you can see that either are, and there if suppose there will be bacteria, there will be some microbes which will be converting directly this bicarbonate into, if HA are not present and HOM are present, that is hydrogen oxidizing methogens, then this bicarbonate will be directly converted into methane. Complex organic matter is converted into methane and inorganic carbon. So this is overall process. Okay, this is known as, this is our hydrolysis. This is our acid formation. This is our acetate formation, and this is our methane formation. So see, that is a simple reaction. This four simple reaction, and then this. See the beauty. Means if you want to explain, if someone is more curious, he will look into this thing. If someone just want to know what is anaerobic, you can explain that thing. You can, for your convenience, you can just take a screenshot. So that's all. We have still have 8 minutes. So if you have any kind of doubt, just ask me, or we can end the lecture here. I am from generally. Does anyone remember that last time I have shown you my lab? Does anyone from my last lecture is here? Anyone from last lecture? I don't know. I don't recall anyone. Dr. Ishti, Dibyan, Varu, Akash. Hi, so okay, we have around 5 to 6 minutes. Let me just simply give a overview of my lab. So I am from environmental engineering department. So, and I'm okay. So so see, my any doubt, Dibyani? If you have any doubt, you can just if you are asking, saying something, I will.
Uh,
Huh.
yeah, yes, sir. Calculate the CUD remove by reactor. When we calculate, uh, the reactor remove the 85% of CVD from the influent. This statement actually gained by the reactor, or uh, we assume that statement.
No, we did not assume that a statement. It was in question. 80% is in converted into biomass, and 5% in biogas, and 5% in biomass. Here,
Okay.
given
So,
question.
so when the question, if we don't have a biogas and biomass, we can't calculate the volumetric load of the COD.
For volumetric load, we don't need this biomass and volumetric load. We just only need how much COD is coming,
Huh?
and what is the flow rate, and what is the volume of our UASB.
Uh,
We need this percentage to calculate the COD, how much COD has been treated.
okay. So when we calculate how much COD is treated, then we have biomass and biogas both.
Yeah, see, miss, in question it is written that like, see, influent is coming, effluent is going out, and in
Okay.
question it is written that 85% are getting converted into biomass. Means whatever is coming into our system, that is 1200 is incoming, is 1200 which is coming in our system. Out of 1200, 80% are getting converted into biogas, and 5% are
Uh,
getting converted into biomass, and remaining are going out from our system. So that this is the
um,
concept which I have used.
in which question the biogas and biomass is in a percentage form.
Yeah,
So when these value are in the form of grams, so how to calculate, sir?
no. See, we are not seeing. Just we are looking into percentage. There might be a
Okay.
third thing which can be also happening. But in question they are saying that 80% is going in the form of biogas, and 5% is going in the form of biomass. Means total how much removal has occurred.
Yes, sir. The question was I understand, but when this biogas and biomass values are not in the percentage, if is in the form of a gram or kg, so how can I calculate?
Then see, suppose instead of this saying that 5% biomass is there, suppose, then some other data will be also given to you, okay na. Suppose instead of
Okay.
saying that biomass 100 kg biomass has produced, yeah, 100
Ah,
kg,
yeah.
then some other data like at other data like see, miss, you don't be given any unknown things. Right now, I'm not recalling. Suppose instead of 5%, if it is saying that, suppose it was saying that biogas, this much kg of biomass, by kg of biogas is produced, and by kg of biomass is produced. Then in question,
Okay.
it must be written that, miss, it is like come. There will be some third data which will be given to you, that can be interpolated, and you can find out the percentage and all these things. Maybe in that case, a direct efficiency, total efficiency will be given to you, and maybe a unknown COD will be. See, a nice question can be produced like. It can be said that this much kg of whatever COD is coming, out of that, and flow will be given to you, miss, flow rate will be given to you, and it will be given to you that uh, uh, biogas which is producing is by kg per liter, and biomass which is getting produced is x kg per meter, and efficiency
Okay.
of the USB is this thing, and outlet effluent will be given to you, and then you can calculate the influent COD.
Sir, can you provided variety of questions, numericals that can help us to exam?
See, right now, just wait a
Because
minute.
in a assignment, a 7 week assignment, I solved this question, biogas and biomass. Actually, when I was solving this question, I refer the more books, but I can't understand this question.
Similar type of question was there, yeah, some other questions.
Similar type of question. In this question, the data is assumed that 1 kg of COD loaded in the reactor produce the 50 gram of biomass and 800 gram of biogas, while remaining COD goes out with the influent based on the information. Answer the following question. So when this question in which the biomass and biogas are in the form of gram.
Hmm. So you can.
Uh, so
Huh.
so my question is not related to your question, and I am very confusing. That's why
In which week this question has appeared?
7 week assignment.
Just let me just one.
Sorry.
So this is
No, it's a 6 week assignment, sir.
week 7.
Week 7 assignment last date is tomorrow, sir.
Why I'm not getting week number 7? Just let me once. This question.
Yes, sir.
SB required to treat 6 mld having itna COD at volumetric loading rate. So here see volumetric load is given to you. See, it is the reverse of the first question. So from here you can calculate the volume. Okay, assume
Yes,
one
sir.
1 kg of COD loaded in the reactor produce 5 kg of biomass, 50 gram of biomass and 8 gram of uh,
Biogas.
biogas, while remaining goes out based on effluent COD of the treated effluent. So here
Yes.
what? So here you can see that see here it's percentage only 1% of this 1000 kg of COD loaded, 1000 gram of COD loaded is getting at 800 gram is converted into biomass. Means how much percentage is getting converted into biomass? 80%.
800,
800.
80%.
50. Same question is there. It's just in kg and that is in percentage. If is here efficiency is also 85% only. See, just
Okay. Okay.
got it. Here
Okay.
both are same question. See it.
Okay, sir.
Say here it is saying that 100 kg COD. There you have miss. You can just imagine 1 kg COD is there, and it's simple. Same question is there. I don't think any miss. It's just a different way of representing it.
Okay, sir. Okay. Okay.
Huh.
Uh, okay, I do it again, and then I will answer again.
It's same question.
I solved this question, but I think I missed something, and
It's
actually I write this question and then I solve this question in my notebook, and I can't understand the 1 kg and biomass and biogas requirement and how to calculate the COD. Okay, I will solve
it's
this
just
question
another way
again.
to see. It's just another way to represent the efficiency. Okay, na efficiency is
Okay.
85%. From here you can just see efficiency is 85%, and just you can
Okay.
have a screenshot of the solution. I hope
Yes, sir. I have a screenshot of this solution.
do it. Okay, na.
Okay, sir. Yes.
Any another doubt? So it's already 9 past.
No, sir. Thank you.
Okay, so those who were saying that you want to see my lab, I will request you to please attend our my next session. I will surely show my lab. Okay, na. So but right now it's already 9 p.m. Okay, so I will request everyone to join next week also. Thank you. Good night. I'm ending the session.